welcome back to the afternoon session. It's my pleasure to introduce Eric Weinstein, who's going to tell us about some variations on that theme of Faltings.
Thanks so much, and thanks to the organizers for this fantastic workshop. This is going to be a project at the intersection of p-adic geometry and homotopy theory. I think these topics have a lot to offer each other, for sure. Much of this topic was inspired by conversations I was having with Andrew Sanger about the chromatic splitting conjecture, and then we proposed a workshop at the American Institute of Mathematics last December, and I want to be sort of maximalist about who contributes to this project, so there are some collaborators. In particular, Lucas Mann will sort of continue this topic in his talk on Wednesday. Let's get started. I understand that maybe there are not a lot of experts in p-adic geometry or so much. If you want me to explain more details on anything, please interrupt. I'm going to start with a strange kind of motivational problem. Consider the following complex analytic spaces. One of them is going to be the open unit disk, so all of the complex numbers of absolute value less than 1. And the other is going to be the upper half plane, all of the complex numbers whose imaginary part is greater than 0. And then it's a pretty well-known fact that D and H are conformal via the appropriate Mobius transformation, right? And my question is there an analog of this where the complex numbers are replaced by the p-adic numbers? Is there an analog of this over, and let's say I do CP, and CP should refer to the field of p-adic numbers, and then take the algebraic closure of this, but then that's not p-adically complete, so you have to p-adically complete it. So is there such an isomorphism? And I claim that there is, and this is what I'm calling Faltings' two towers isomorphism, although I don't think Faltings really put it this way. Okay. And yes, there will be homotopy theory. You just have to wait slightly for it. Okay. Spaces. So before even being able to pose this question, you need to say what the analogs of D and H actually are. And so one thing that might be tempting is to say that the analog for D might be something like this, just everything close to 1. Close to 0 with radius 1. So maybe it's all of those elements of CP. CP is a metric field, so it's perfectly good to say that the absolute value of Z is less than 1, right? It makes sense. The problem is it doesn't have very good properties that you would expect from a ball or a disk. It's not even connected. So that's an issue. If we want to do some kind of analytic geometry with such a space, it would be great to have something connected. Well, this is what prompted Tate and then Huber to invent new theories of non-Archimedean geometry to kind of solve this issue that you want to do kind of geometry where a space like D should be connected. So I'll try to be very brief about how this goes. I'm going to consider OCP is going to be the ring of integers in CP, all elements with absolute value less than or equal to 1. And if I were to consider the power series ring over this in one variable, what I want to do is consider this as related to the disks that I care about. These are all the power series that converge on the disk D over here. So for each one, for all Z in CP, such that Z is less than 1, you get a map from the power series ring to non-negative real numbers, like this, where the power series gets mapped towards, well, you just substitute, and then take the absolute value. So CP is a metric field, so this is allowed. So this thing, I'm going to call this a valuation. It's a way of valuing elements of the power series ring, and it satisfies some properties. The absolute value, so let me just call this thing absolute value of F. And it satisfies, well, the absolute value of 1 is 1, the absolute value of 0 is 0, the absolute value of f times g is equal to f times g. The absolute value of f plus g is less than or equal to the maximum of the absolute value of f and the absolute value of g. In other words, this is a kind of non-Archimedean metric. And then finally, the absolute value is continuous in some sense. The preimage of some interval inside of the real numbers should be an open subset of that topological ring. So the form of non-Archimedean geometry proposed by Huber is to say, well, let's consider all such valuations, not just the ones that come from elements of this set. There are going to be others. So such a thing, and it doesn't even have to be valued in the real numbers. If I take the positive real numbers and I replace with some other totally ordered abelian group, such a thing is called a continuous valuation. And you can consider all of the continuous valuations of such a topological ring to get a new sort of geometric object, and that's what's called an adic space. There's going to be a lot of them. In fact, there's going to be some that are more like the subnorm on a subdisk here. Those count. And then furthermore, there's going to be valuations where you really need a higher rank abelian group of rank 2. Bigger than R, to get really all of them. The notation that gets used for this is SPA, like the adic spectrum. It's meant to remind you of the usual spectrum in algebraic geometry, and so I could write such a thing like this. SPA of OCP double brackets U, that's going to be all of the valuations up to an appropriate equivalence relation, which I'll leave it to you to imagine what it is. This is going to be some huge space. It's not going to quite be the analog for D that we want, because some of the valuations think that the number P has absolute value 0. And we want just the ones that think that the absolute value of P is non-zero, so we get an object which really just lives in characteristic 0. So the analog, for the correct analog is what I might call dP, and that's going to be all of those valuations that think that the absolute value of P is not equal to 0. They have to be continuous valuations. If you want, you can think of the absolute value of P as being, as it usually is in p-adic analysis, it might be 1 over P. And if you fix it that way, then something cool happens that you would expect to happen. There really is a map from dP.
Do you want to exclude the ones where P is non-zero or 0?
Oh gosh, yeah, thank you. Yeah, you have to throw away the ones that think that P is equal to 0. Once you've done that, then you can set the absolute value of P to be whatever you like as long as it's less than 1. It has to be less than 1 because in this ring, P is topologically nilpotent, and these valuations are supposed to be continuous. So the absolute value of P must be less than 1. You might as well assume that it's 1 over P. If you've done that assumption, there really is a map from dP, which is supposed to be the unit open disk around the origin, towards the half-open interval, this one, where you just send an absolute value towards whatever the absolute value of U is. And the cool thing about this is that, okay, you can make dP into a topological space. This is going to be a continuous map, and in fact, it's surjective. So this dP, it's interesting. It's a locally spectral topological space. It's not Hausdorff, but it's pretty big. Check it out. It has a surjective map to this interval. So once you really understand this example, you've gotten a feel for some aspects of non-Archimedean geometry. These are the sorts of spaces we work with. Questions so far? Okay. Yeah, really fascinating subject. I know.
So are you saying that you're normalizing these things such that they all have the property that the absolute value of P is 1 over P, or is that just what you're saying is for the traditional valuation on the p-adic?
Once you've assumed that one such element is not,
Yeah,
this is really
on
up to
DP,
equivalence relation.
No, yeah. But on DP, on DP, you can make that happen.
On DP, you can make it happen.
Very good.
In other words, DP is fibered over the same thing that you might do on QP. And then on this one, there's just one, this just has one set. Okay.
Excellent.
All right, so in the interest of time, I'm not going to say exactly what an adic space is, but here's my attempt. Generally, an adic space is a topological space X together with a sheaf of functions, just like a scheme would be. There also has to be a sub-scheme of functions. You could ignore this from now. Sorry, a sub-sheaf. Those are functions bounded by 1, and this is called OX plus. Which looks locally like a certain model space, and that model space is like this SPA. The model space, it's SPA. Really, SPA is supposed to take 2 variables, a ring and a subring. A here is a certain kind of topological ring called a Huber ring. And that means that, so Huber rings, that's a full subcategory of the category of topological rings. So when is a topological ring a Huber ring? It's got to have this property. There's a subring that's open, and an ideal inside of the subring that generates the topology, and that ideal is finally generated. So it's finally generated, and it generates the topology on A0. And okay, that's a lot of symbols, but it gets across this idea that, A itself doesn't have to be linearly topologized by an ideal, because that would exclude a really important example of QP. QP is not literally p-adically complete, because the only ideals in QP are 0 and the whole thing. But QP contains a subring, ZP, and then ZP, its topology is p-adic. So that pattern really fits into this framework. That framework's really, really flexible and allows you to do analysis in a lot of different situations. So there you have it. This is basically what an adic space is. Okay. So these were developed by Huber, but really generalizing work of Tate and then Berkovich also. Okay. So are we ready to talk about the Faltings isomorphism? Yeah, why not? So, oh, I didn't say what this was. Well, just think of all of the continuous valuations on A that take the absolute value less than or equal to 1 on the subring A plus, which you specified. I wouldn't worry about that right now. A pluses. All right, so over here, oh wait, should we just not use this because of this thing?
It won't hurt.
It won't hurt. Yeah, all right. Oh, where's the erasers are there. Very good. Right, so I wanted to propose that Faltings' isomorphism actually answers the question that's on this board. We need the proper analogs of the D and the H. The D, maybe you've just seen one, but actually I want an example, I want an answer to this question in all dimensions. So not just one dimensional, but every dimension. So I'm going to fix a prime P. Okay, I think we already did that. Talking about Faltings' isomorphism. So we fix a prime P, sure. Let's also fix an integer n, at least 1. And I'm going to let k, just as an abbreviation, I want k to be the algebraic closure of Fp. And then here I'm going to do this thing familiar to chromatic homotopy theory, which is that I fix a formal group. I'm going to call it gamma n. So this will be a one-dimensional formal group of height n. there's only one of these up to isomorphism. And the next stage of this is to write down the Morava stabilizer group, which I understand is important to the chromatic homotopy theory people. I'm going to write that as Gn. So this is the automorphism group. So as I understand it, this is sort of the biggest version of the Morava stabilizer group. It's the automorphism group of not just the gamma n, but really the pair, k, comma, gamma n. This is some profinite group. It's a cover of Z hat by a certain p-adic Lie group. Okay. So this Gn acts on sort of both the k and the gamma n. And then the next thing is to consider deformations of this gamma n. So I want to make a notation like this. An, it's going to be the Lubin-Tate ring. And there's a few other descriptions of it. The one most familiar to people in this room, I think, is that you consider Morava E theory and just take its pi 0. So this is the deformation ring of gamma n. And a description of it in terms of what it actually is as a ring is that this thing is isomorphic to the ring of Witt vectors of k. And then I do a power series ring, u1, u2. The last one would be un minus 1. So now we see a power series ring appear. Yeah? Okay, so that's Morava E. Morava E theory, and the Lubin-Tate ring appears as pi 0. So the analog of the D that I'm now erasing is going to be something like the adic spectrum of this ring AN. Oh, is that better? Oh, this one is much better. Okay, I'll use this one then. The microfiber cloth. Okay, so this AN is a topological ring. It is a Huber ring because its topology comes from a finitely generated ideal, namely the ideal P U1 all the way through UN minus 1. And it admits a continuous action of this Gn. So that's the setup here. And the analog of the D that I want to consider is what I'm going to call Lubin-Tate space n comma 0. For one, I can let LTN simply be the adic spectrum of this ring AN. If you think of AN as just the power series ring, then it formally resembles this example. You can consider all the continuous valuations on this, but some of them will be characteristic P points. When you delete all those characteristic P points, what's left over is a characteristic 0 space that I'm going to call LTN comma 0. So that's like this DP. It's like the open unit ball over a base of dimension n minus 1. So let me write that. Open unit ball of dimension n minus 1 over the base. Okay, what's the base? I guess it's the Witt vector ring invert P. It's that p-adic field, this one. So, geometrically speaking, that's all it is. It's just this ball. The ball admits this action of Gn. So that's going on one side of Faltings' isomorphism. What's on the other side? Some kind of analog of the upper half plane. So what's that analog? I'm going to write it as Hn minus 1. So this is Drinfeld's symmetric space. It's a subspace of projective space defined over the p-adic numbers. But I want to consider this whole thing as an adic space. I have to delete from this some portion. It's the portion consisting of all points which live in a hyperplane, which is QP rational. And, okay, that's a bit of a mouthful, but at least in the case of n is equal to 2, I can give you a pretty good description of this, and then also you can see why it's a good analog for complex upper half space. So in height 2, this h1, it's p1 over qp, but then, you know, there's no hyperplanes, they're just points. So imagine deleting from this all qp rational points. So, okay, this is not a typo. I mean, this is p1. You know, the points of this are these bizarre continuous valuations on some rings which make up this p1. And I have to delete from this all points that truly come from a valuation at a rational point. And this is an analog for the usual upper half plane, which if you think about it is just the Riemann sphere. Take away the real points of the Riemann sphere, although when you do that, you don't just get the upper half plane, you get the upper and lower half planes. So these together. Furthermore, the Drinfeld symmetric space, you know, it has a lot of symmetries. The condition of being in one of these H's is QP linear, so it has an action by the group GLN QP. It just acts linearly on this projective space, and it preserves the locus that we've deleted. So that's going on the other side. Okay, so I can now tell you what Drinfeld's isomorphism, sorry, what Faltings' isomorphism is. So I'll write it this way. So Faltings wrote something about the isomorphism between the Lubin-Tate and Drinfeld towers. It wasn't going to be in the form, it's not going to be in the form that I'm about to write. For more explanation on how to translate Faltings' result into ours, I will refer you to my paper with Schulze about the moduli of p-divisible groups. And then in the present form, there's the paper by Bartel, Schlock, Stapleton, and myself, but the second paper in the third chapter of that second has everything you might need about this. And the isomorphism is between two stacks. So on the one hand, there's LT n0, which, by the way, just a ball. Ball of dimension n minus 1. I have to quotient this out by the action of Gn. On the other side, there's Drinfeld space, Hn minus 1. And I'm going to quotient out by the action of GLN ZP, the compact group, GLN ZP, not QP. These stacks are isomorphic. I have to do a certain decoration. Don't worry about it for right now. It's a little diamond. I'll explain what this means in a second. But before that, just understand that this really is an analog for the statement from complex analysis from before, because this is a ball and this is Drinfeld upper half. This is like upper half space. They're only become isomorphic up to the action of various profinite groups. That's it. Okay. What's going on? All right, so I have some commentary about this. First of all, what is this diamond supposed to mean, and what are these stacks even supposed to mean? So the diamond means for an adic space X, which lives over ZP, X diamond is the restriction of the Yoneda functor of X. Before I finish this sentence, what do I even mean so far? Any object in a category defines a Yoneda functor from the category it lives in to sets. Great. Take that functor and restrict it to a certain kind of adic space. That kind of space is called perfectoid space. Those are Schulze's perfectoid spaces. Am I going to define them right now? Nope. But if you really demand it, you can ask right now. Or I could just say a couple sentences like, you know, adic spaces over QP, they've got some problems. They're not even locally contractible. In the way that a disk or a ball in complex geometry, that's contractible. But in p-adic geometry, no matter how small you make the ball, it's still not contractible. However, in some sense, when you pass from such objects way all the way up to these infinite covers, they become contractible in the sense that we need. those objects are examples of perfectoid spaces. And that's why it's sometimes a good idea to work with those as the kind of model category for all of these fancy objects. Okay, that's what X diamond means. What do these stacks mean? Well, the perfectoid spaces, that category has a topology, and that topology is called the V topology. What does that mean? The V stands for evaluation. That's not very helpful. The V topology is an analog for the flat topology or the FPQC topology on schemes. It's a very fine topology that really works well with various descent problems that you might want to do. So this kind of quotient stack is computed for perfectoid spaces under the V topology. I guess I'm giving Lucas a lot of, well, the V topology is in Lucas's title on Wednesday, so probably he will talk about this a little bit. Okay, so more to come later. Okay, so this isomorphism of stacks. I should also discuss why such a thing is true. Like, why does this theorem hold? And I can't say every detail, but first of all, what is the moduli interpretation on the right? So it's formed, it seems, from projective space. So this classifies for a test object S, something like lines in an n-dimensional space, or line bundles that are like, I'll write them as W, and they're going to be inside of n copies of the structure sheaf. So a sub-bundle of OS to the power n of dimension 1. That's what this projective space does. What would this stack mean? Now I've modded out by this action of GLNZP. And this classifies, if you like, pairs. So we were kind of like removed the basis from this by doing so. And oh, I realize I'm writing, let's write higher. Pairs T comma W, where T is a ZP module of rank n. So it's abstractly isomorphic to ZP to the n. And the W, again, is going to be inside of T tensor OS over Z, like that. So there's some kind of abstract definition of what this quotient stack is supposed to classify. So this definition with the T and a W is supposed to remind you of Hodge structures. So the T is like an integral Hodge structure. When you tensor it up with a bigger base like this OS, this line appears inside of it. So it's like a Hodge structure, and that should correspond to some kind of geometric object. That geometric object is going to be a p-divisible group. Sometimes the p-divisible group comes from a formal group when your element of projective space actually lived here. I know that's a lot. But I could spend the entire rest of the time talking about the details of this. If there's any particular questions about this isomorphism, I will take them now.
This isomorphism here?
Oh yeah, this one.
I do have a question. Is there a relationship between this and the Gross-Hopkins period map?
There sure is. The question, is there a relationship between this and Gross-Hopkins' period map? There is. It doesn't involve the projective space from here, though. Maybe I can just write the whole picture. Another way, the way that Faltings originally operated was that here's Lubin-Tate space over here. There's some huge space, LT, N0, but then ad infinite level structure up here. And then there's some other space, and that's Drinfeld space mapping up here. And both of these are torsors for the various groups. Here's, this one would be the GLNZP, and this one would be the GN, like so. So another way of stating the isomorphism is that there are these two covers, and this modulo this is the same as this modulo this, right? So you asked about the Gross-Hopkins period map. That's a surjective map onto projective space like this one. So that now this is actually a cover of this. It's a torsor for the action of GL and QP. There. So that's how that fits into the picture. So this is the Gross-Hopkins period map. So it's kind of on the other side of things. So just as the Gross-Hopkins period map was invented for homotopy theory, there's going to be an application of this isomorphism to homotopy theory as well. So let's switch the words.
Say anything about how such a Hodge structure, TW, produces some sort of definition of formal groups?
So, all right, yes, you should actually finish this sentence. So this Hodge structure produces a p-divisible group. So if you look up the paper of Schulze and myself, then you find that at least over a base like CP, such a pair actually produces a p-divisible group which lives over whatever base you consider. In this case, it'll be OCP. P-divisible groups contain formal groups as a subcategory. So you then have to ask, under what condition the p-divisible group you got was formal? And that condition is exactly the condition that this W is not contained in any QP rational subspace of this. If it were, you would find that your p-divisible group admits a non-constant map to the étale or the constant p-divisible group. So those are, you just have to work that out. And if you want more details, may I refer you to BSSW section 2, part 2, section 3, has all those details. Okay, so I want to switch into homotopy theory now. We've already been half an hour. Okay, oh yeah, got it right here. All right, so I want to tell you about applications of this stuff to homotopy theory. First, I'll tell you about the applications that occurred in the first paper of these authors, BSSW, and then I'll tell you about what comes next. So, I need another stick of chalk. So, applications to homotopy theory. So, in brief, Faltings' isomorphism was leveraged, was used to prove, okay. So this is the main theorem of BSSW, the first, which is that if I look at the Kn local sphere, and I take its homotopy groups, well, these are still a little bit mysterious, but after inverting P, in other words, tensoring with Q, all right, well, this was P complete. So after tensoring with Q, it should be a QP vector space, and I just want to write it quickly like this. QP adjoins some variables. This is supposed to be a graded ring. This means the exterior algebra over QP with the indicated generators, and the ith generator has degree 1 minus 2i. So it's a computation of what the homotopy groups of the rationalized K of n local sphere are. So this had been known previously in the n equals 2 case, and we used Faltings' theorem to get all of the rest of the cases. So, all right, so how is this done? So first of all, I want to reduce this to some kind of algebraic statement only having to do with group cohomology and not having to do with spectra. So the Devenitz-Hopkins spectral sequence came up in Ishan's talk, so I can just refer to it. So So that spectral sequence relates the homotopy groups of En, then take cohomology under Gn, to the Kn localized sphere. So the statement that we want is something like this after inverting P. So what does this mean? So Gn acts on An continuously. If you have a group acting continuously on a topological group, then we can take the continuous cohomology. The result of that is going to be a ZP module. After you tensor with Q, or Q, you don't have to tensor with QP. You can tensor with Q, and now it becomes a QP vector space, and I just want it to be the same as this one. Although now I need the degrees of these things to be flipped. Or maybe not. It depends on how you think about cohomology and how it's indexed. But the way that I'm used to, I want this to be positively indexed. All right. Okay. I think it's plausible that Faltings' isomorphism could be used to prove this, because after all, the thing on the left seems to be related to the thing on the left up there. So we're quotienting in the LTN0, which was derived from AN, by the group Gn. So somehow the thing on the left, when you take its cohomology with some kind of coherent cohomology of it, you should get the thing on the left. So I'll make that explicit now. I don't want to erase Faltings' theorem. All right, so the left-hand side, and I mean the left-hand side of the theorem. This is related to the O plus cohomology of the stack LTN0 modulo Gn. So,
Which theorem?
left-hand side of, let me just write this as star, and then I mean the left-hand side of star. How about that? So remember that adic spaces, they have a structure sheaf O. They also have a subsheaf of integral functions, or functions bounded by 1. That makes a big difference. So on the open unit ball, there's many more O functions than there are O plus functions. The O plus functions on the space LTN0 just produces AN again. So we're using the fact, I'll just write it here, that AN appears pretty naturally as the global sections of O plus on this open unit ball. So, I mean, it kind of goes both ways. I mean, LTN was formed by the SPA of this AN, but you could recover AN back from LTN0 just by taking the global sections of O plus. I guess this is some kind of calculation. You have to say, oh, if I have a power series in n-1 variables, and it converges on the open unit ball, and it's less than or equal to 1 everywhere, then all of the coefficients have to be integral as well. That's the point. Okay, that's the left-hand side. What about the right-hand side? The right-hand side is related to, again, the O plus cohomology, but of the other side. So that's going to be the quotient of Hn minus 1 by GLN ZP, whatever that comes out to be. So the way that the logic progressed was, we need to figure out what the cohomology of that stack is with coefficients in O plus. So there were a couple of key calculations. One was a calculation of what the cohomology of just Drinfeld space is with coefficients in O plus, but let me just take that Drinfeld space and for simplicity base change it up to an algebraically closed field so that what we're doing comes a little bit closer to geometry rather than arithmetic. So there are tools for calculating such O plus cohomology, and by the way, we're doing everything in the V topology. I'm not even notating that. So there are tools for doing this kind of thing. Those tools come from the work on integral p-adic Hodge theory of Botmar and Schulze, and its extension to the semi-stable case offered by Cesnavicius Koshikawa. Okay, we would not be able to do this material without those contributions. So after inverting P here, actually there's not so much going on. The resulting thing is just CP. So basically this Drinfeld upper half space, when you take its coherent cohomology, there's not much doing. It's acyclic. And that seems to be the pattern that I'm hoping continues into the other objects I will introduce in a second. But that was part one, this kind of acyclicity calculation. The second important calculation, well, okay, think about this. If I want to compute the cohomology of a sheaf on a quotient stack like this one, I should take the group cohomology of whatever group it is, acting on the sheaf cohomology of whatever object it is. But there is no interesting sheaf cohomology there, it's just constants. So as a result, one's left with the computation of the cohomology of just the group with coefficients that are constant, like this one, QP. All right, so what's that? Well, this was worked out in the 50s. So this is Lazar. Well, Lazar gave wrote a whole book on how to compute the continuous cohomology of p-adic Lie groups with, coefficients where p is invertible at least. And those techniques tell you exactly what you expect it to be, which is that it's QP, exterior algebra, and N generators, just as was expected. So, I don't know, in broad strokes, how was this theorem proved? We use Faltings' isomorphism, that one, and then we compare O plus cohomology on both sides. As an intermediate step, we needed an acyclicity result for Drinfeld space, and then we needed some kind of Lazar result that was just about continuous cohomology. Okay, before going on, are there any questions on this stuff? Because we're about to exit this case.
What's the degree of xi to I minus 1?
Oh, sure, same. Yeah. 2I minus 1. This is very interesting material. It's been a real pleasure to study this stuff. It goes through a lot of twists and turns, but eventually you get to a Lie algebra cohomology calculation of the Lie algebra GLN, which you can then compare to the de Rham cohomology of the compact form of that Lie algebra, which is a unitary group, UN. And then the de Rham cohomology of UN is sort of well known because, UN, rationally speaking, it's like a wedge of a bunch of odd dimensional spheres, S1, S3, all the way to Sn. And that's where these generators come from. But there are a lot of twists and turns to get there.
So the chromatic splitting conjecture suggests that xi should in some sense have height n minus I.
Yes, I'm so glad.
Are you seeing any sign of that?
Let's find, yeah, that's exactly, you really anticipated what I'm going to write next. So I'm going to now talk about some kind of Hopkins' splitting conjecture, okay? So I think I can erase this now. And the next phase of this is to kind of generalize what was just done in the theorem I just erased. All right, so let's call this. Okay, I don't know. I've been discussing with somebody what to call this. I think in Copenhagen it was transchromatic, but then now it's just going to be bichromatic. I have no idea what to call it. I'm going to call this bichromatic splitting. It needs to get across the fact that there's only two colors involved. Okay. So the prior theorem was about the k-localized sphere, but then rationalized. But another way of writing that is just the k is 0 localization of the kn localized sphere. So that really suggests like a next phase of this project where you allow any other height going here, as long as it's less than this height. So I'll pose a conjecture here, and I'm going to call this the bichromatic splitting conjecture. Okay, I'll write it out just this once. Splitting And it follows very quickly from a strong version of Hopkins' splitting conjecture. But it just has to do with what you expect this kind of double localization to be. So I'm going to assume that t is between 0 and n strictly, and I'm also going to assume that p is pretty large relative to n, which is maybe kind of disappointing for topologists because they're very interested in how small primes like 2 behave. But first, let's do the generic case, the case that resembles geometry a little bit, where you can do more algebraic stuff. So this should be isomorphic as a ring spectrum to, all right, some number of copies of the k of t localized sphere. So I want to write it as follows. I want to take this ring spectrum and tensor it with a graded ring that's just, yeah, I'll just write it this way, z and then x1 through xn minus t. So this means the exterior algebra in just these generators, where the xi have to go back to the other convention where they're negatively indexed. But what does this mean? So this is a free z module, which has a grading on it. So for each copy of z that is here, put this thing and suspend it this amount. So, you know, this is spanned by a bunch of monomials in the xi's. So each time you see one, take the degree of that monomial and shift this thing appropriately, then add those up together. The result is actually going to be a ring spectrum. And the splitting conjecture, as I'm putting it here, is that this is an isomorphism. However, well, okay. Well, I'll just state here that this is a consequence of the conjecture of Hopkins. And that conjecture concerned not this kind of double Morava K3 localization, but rather the localization at, basically at En. I mean, this is, so when I write Ln minus 1, that means localization at Morava E theory of the Km local sphere. So Hopkins proposed the way that this should split. And if you take Hopkins's formula for how this should split and k of t localize both sides, you would get this. So what we're investigating is a consequence of this sort of splitting conjecture. So I want to understand what p-adic geometry might have to say about this situation. Okay. All right, so now I'll switch the boards. So just as in the project where t is equal to 0, I want to be able to reduce this to some kind of algebraic statement which you can then approach using p-adic geometry. So that algebraic statement should be posed in terms of continuous cohomology of the Morava stabilizing group, this Morava stabilizer group acting on something. So right underneath this conjecture, I want to write a different one, which is like the algebraic version. The algebraic I need more shock. BS, bichromatic splitting conjecture. How about that? So this has to do with the continuous cohomology of the same Morava stabilizer group, but this time it's acting on something else. So you should take AN and mod out by a certain ideal. So this is under the same assumptions as the conjecture above, by the way. The ideal will end at t minus 1. And since it's like we've k of t localized, so somehow ut, this height t operator, should be inverted. So, okay, what's that? And this should be isomorphic to something else. So that's something else I want to phrase in terms of the group cohomology of a completely different group. So this was a statement that arose in my conversations with Andrew Sanger some time ago. The group that should appear is a copy of the Morava stabilizer group at height t, and then this other group appears, GL n minus t zp. And the coefficients should be in fp. So notice that this really kind of generalizes what happened at t equals 0. When t was 0, this group disappears, and you get the group cohomology of GLN, although it has QP coefficients in that case. When t is intermediate, you kind of get this blend of two groups, GT and GLN minus t. And so it seemed plausible to the topologist, and especially Andrew, that this group should appear, but now I want to tell you why it should appear because of p-adic geometry. Okay. So as a remark, I want to say that the algebraic version of this actually does imply the topological statement in the case t equals n minus 1. And this case seems like the most tractable case to start studying, because in that case I can actually write down a map for you from the right side to the left side above. I think there was a comment about what all the xi's actually mean. In the case of t is equal to n minus 1, there's only one generator up there, and that comes from a determinant. And in that case, you actually have a map. It's way easier to find an isomorphism when you actually have a morphism. Otherwise, I couldn't tell you a canonical map from one side to the other. Yeah. So this is a good case to start with. Okay. All right, so now the question is, where did that group come from? And you know, this sort of project it's all work in progress, but we can at least answer this question. All right, so I'll put this here. All right, so beyond Faltings. All right. Remember what I had written about Lubin-Tate space at height n. So this was some adic space. It's affinoid, meaning it's like affine. It comes from just one ring. And that ring is an, and that ring can also be written of vit vectors adjoin some parameters u1 through un minus 1. And within this, there was a subspace, the space where the first parameter p is not equal to 0. And that space appears in Faltings' isomorphism. It's the open unit ball over the base w of k invert p. But you could also imagine other spaces. So what if you consider LT and T? So this T now becomes an intermediate variable. What should it mean? You allow, okay, so this will be when T is greater than 0, and you can have it go all the way up to n. So this should mean that the absolute value of P actually is 0, as is U1, all the way up to UT minus 1. And UT should be not 0. So this definition makes perfect sense. It's a locally closed subspace of LTN. I suppose when t is equal to n, you just drop this last condition because it doesn't make any sense.
So it's kind of a stratification of the Lubin-Tate.
That's exactly what it is. It's a stratification. It's a really natural one too. So LTN is a disjoint union over t goes from 0 to n of LT NT. And by the way, the Murata stabilizer group preserves the stratification. So we've really stratified the stack LT modulo GN. And to me, it's like pretty clear that these things are the important players in the study of this algebraic conjecture. All right. So I'll write down the theorem and then add. Okay, so I want to preserve this board for sure. I guess, yeah, you have to be, if you're a speaker and you're not very tall, you have to be very careful about making the board too high, because then you can't reach it. Just discovered this. So, the theorem in progress that our group is working on has to do with the stack. Okay, I guess you could predict what the left side of the stack is going to be. Because at first we had LTN0 modulo GN, now I just replace the 0 with the T. And so this kind of quotient stack should be related to what's going on the left side of the algebraic BCSC. Somehow you've modded out by those variables and inverted the next one. What's going on the right side? Oh, well, first of all, I have to diamondify this. Okay, great. On the right side is some kind of different period space, omega nt, let's call it. And then we have to mod out by the group that we hoped to see. That's gt cross gl n minus t of zp. Of course, we're not saying what this is yet. But at least this group appeared, so that's cool. And then if you could imagine trying to follow the same strategy as was done in the t=0 case, that leads you to ask the question of, when I take O cohomology on both sides, what's going on over here? So you might hope to prove the first result that you needed along the way, which is acyclicity. Something like this, the cohomology with coefficients in O of this omega nt should really just be FP. And perhaps Lucas will be talking about this on Wednesday, I'm not sure. Yes, not sure. Something related to this. Okay.
Does it matter O or O plus?
Right, O or O plus. It seems like, at least in the case n is equal to t minus 1, the O becomes the more relevant thing. In the intermediate cases, it's actually still unclear to me how to make the left-hand side actually appear, although we will hopefully figure this out eventually. So far, we really have a maybe clear manner of progression just in this case, but in all cases, the correct group at least appeared. Okay, cool. What's omega nt and why does it have this action? So, 2 minutes, great. That's okay, I'll be saved by the bell, and if you ask me what any of these symbols mean later, I'll be happy to tell you. The people working in local Langlands have been on these objects for years. So this stands for Banach-Kolmez space. It's got a slope. The slope is -1/t. And I'm supposed to take the direct sum of n minus t copies of it. What is this BC? Well, this stands for Banach-Kolmez space. As the Banach in it suggests, it should be some kind of normed vector space. In fact, it's a QP vector space object in the category of diamonds. Although I didn't quite say what a diamond was. It's like a algebraic space in the world of perfectoid spaces. It's a perfectoid space modulo a pro-étal equivalence relation. But I guess if on first glance, just focus on the fact that it's a QP vector space object. What's this thing? Well, it's the complement of all QP rational hyperplanes. And so I can actually do this with any vector space object in whatever category I want. I can take some number of copies of it, add them all together, and then remove all subspaces where there's a QP linear relation the result is that you'll always get an action of this group. In fact, you could put QP there because this preserves everything. Meanwhile, this GT, well, this GT acts on this quite naturally. So this group naturally appears here. And so we have at least a foothold in solving the algebraic BCSC. If we succeed in t equals n minus 1 case, I'll be pretty happy. Minus 30 seconds. Okay, thanks.
Do you have any questions?
In this case, is there also like an intermediate modular problem that's a span over like in the
Yeah. Yeah, in all cases, what you can do with this LTNT, well, since that diagram's right here, I might as well use it, yeah? There should be a kind of diagram like this. This one. And instead of GLNZP being here, it really ought to be GT cross GLN minus TZP.
That's unbelievable.
I'll briefly explain why.
And you use a different color?
Oh, I guess it doesn't show up. All right, sure. I just wanted to make a contrast with what I was writing that was new. All right. So there's GT. Well, it's the same group that appears there. GL N minus T ZP. I'm sure that's illegible.
It's easier to read if you're red, green, colorblind.
Okay, so what does this mean? LTN carries this universal deformation. We started with some formal group over FP bar, and you can deform it to LTN. Over LTNT, that kind of means that it splits up as something atal, and the atal part has this height, and the rest of it's connected, of this height. But only abstractly. Once you trivialize those, you get this kind of cover. That's kind of exactly how this group appears in this situation. So this appears up here, there's LT and T. When you go down again, you don't see Drinfeld space, you see this omega thing, NT. So that's sort of the other period space that appears, not Drinfeld space. Yes?
There's, so, can you comment about the relation, if any, between the foundations we're using here and the kind of condensed mathematics stuff?
Oh, condensed math is everywhere. I mean, you need it. There was no other way we could have done even the first project without it, because we're very often having the outcome of one of these O+ cohomology calculations. We needed that to have a topology on it. So we need to consider O+ as actually a sheaf of condensed abelian groups. You take the cohomology, then that's going to be an element of D of cond, like a condensed complex. And then it's got a GN action, so you have to consider it as a solid object with an action of GN, and it's just condensed math absolutely everywhere. We couldn't have proceeded without it.
I feel like what you said over here might be hiding the answer to the question I was going to ask. But in the case of t equals 0, the upper half plane parameterized p divisible groups which are formal.
Yeah.
And is there a similar way in which the omega nt parameterizes p divisible groups with certain atal heights?
You bet. Yeah, you bet. The question is, what does this actually parameterize? And I'll tell you, if you feed into this a perfectoid algebra R. Now, by the way, it's purely in characteristic P. Like, to make this LTNT happen, we set P is equal to 0. So everything's in characteristic P. So if R over FP is a perfectoid algebra in characteristic P, you could send this to the set of all P divisible groups H which live over the bounded subring, R circ. And you want these to be like height, you want this to be like formal of height n, such that on the generic fiber, that is, if you tensor it with R, this now has an atal part of height n minus t. That's exactly it. So it's some moduli space for p divisible groups, but they just live in characteristic p.
So the infinite level structure story of when you have T, is it also classified by some of these combinatorial EL type data or something like that?
Oh, this is a little simpler than that. So the EL type that you refer to appears in the theory of Rappaport's-Zink spaces. The E stands for endomorphism, and usually there's some QP algebra which wants to act on the objects. We don't really see that here. We just see QP. The L stands for level structure, so this is what this level structure is. Yeah.
If there are no more questions, let's thank Jared again and have him back.